All right, so let's talk about types of changes. So there's two types of changes, physical and chemical. Physical changes are when the identity of the substance remains unchanged. I've never been a fan of this stuff, honestly. So just bear with me a little bit, and I probably won't stress this on any test or anything. So one thing, physical changes, one way to determine a physical versus a chemical change, physical changes are often reversible. It's not always true. When you cut a stick, both parts of the stick are still stick. So that's not reversible. I guess you could glue it back together, but then you're putting glue in there and whatnot. But when I say reversible, I mean like melting. If you melt something, you can freeze it back to the way it was. If you boil something, you can cool it down back to a liquid. So anytime you break something or grind it up, cut it up, any of the phase changes, like I was just talking about, bending something, ripping something, those are considered physical changes. Chemical changes, what's more important than their chemical changes is how to identify them. So you make new substances out of other things, burning, rusting, molding, rotting, growing. We also call this, and that's the one that upsets me, growing is considered a chemical change. So grass is still grass as it grows, but that's considered a chemical change, not a physical change. And that's where this becomes a little more philosophy, and I don't like getting into it. So, but you do need to know when a chemical reaction takes place. And the way to know that is through these four things. When you make bubbles or a gas formed, that is a sign that a chemical change took place, that there's a chemical reaction. When you form the solid, so look here, we got a clear liquid and we got it going into another clear liquid. So here's a clear liquid and here's a clear liquid, and this solid is formed, and that solid is called precipitate. And a precipitate is a sign that a chemical reaction has taken place. Anytime energy is released as heat or light, that's a good sign of energy, that a chemical reaction took place. And I don't love that this color is so bland, but anytime there is a color change or a change in smell, that's an indication that there's been a chemical change. All right, so the phases of matter you should have learned at some point. If not, here they are. Solid. Solid will have particles close together, definite shape, definite volume, right? The size of my cell phone or my eyeglasses doesn't change whether I put it on one table or a different table. It has a definite shape and takes up a definite amount of space, whereas liquid can change its shape, right? You pour it out from a bottle onto the floor. It's no longer the shape of the bottle. It's sort of the shape of a puddle. And likewise, you can pour it into different shaped containers, and the liquids will just take the shape of their containers. So liquid's definite volume, but doesn't have a definite shape. The molecules are not so close together, or the particles. And then gas is neither definite volume nor definite shape. It takes the shape of the container. And we will do a FET with this, which I really enjoy, an interactive, either in class or maybe from home, one or the other. Okay. So, what do you imagine happens with mass? So, as the mass of something gets bigger, right, it's harder to move around. And because of that, things that have more mass do tend to be solids more than gases. So, if we go back to our periodic table, a lot of the gases don't weigh a lot, and a lot of solids weigh a significant amount. But we'll get into that some more later. All right. So, temperature. We typically measure temperature in Celsius when we're in science classes, um, and we convert it to what we call the Kelvin scale. The Kelvin scale is based on the idea that at 0 Kelvin, there's no particle motion. So what temperature should be measuring is the motion of particles, and it makes sense that at 0 temperature, there would be no motion. So something gets so cold where all motion stops. And so that's why we use this Kelvin scale. And again, when we play with that FET, you will be able to experience that. So at absolute 0 Kelvin or minus 273 Celsius, there is no motion of particles. Any other temperature will have a little bit of motion, whether it's a solid, liquid, or gas, would be regardless. It would still have temperature. So the way you get Kelvin is you take whatever the temperature is in degrees Celsius and you add 273. Examples: if it was 100 degrees Celsius, what would that be in Kelvin? Well, you just need to add 273, and you would have 373 Kelvin is what that is. If you had minus 23 degrees Celsius, you would add 273, and then you would get that to be 250 Kelvin is what that temperature would be in Kelvin. So minus 23 degrees Celsius seems pretty cold to us, but there's still motion, right? It's still significantly above 0 Kelvin. So therefore, there's still motion of particles, even if they're at minus 23 degrees Celsius. All right, these changes in states you should know. Solid turning into a liquid is melting. Liquid turning back to a solid would therefore be freezing. Liquid turning to the gas at any temperature, not at an elevated temperature, we call that evaporation. But if it happens at what we call the boiling point, that is boiling. That's a subtle difference. I'm not going to play games. I'm not trying to trick you on these things. I hope it'll be clear on whatever sort of testing situation we have. Gas turning to a liquid is condensation. So that's what happens on the mirror when someone's in the shower and all that hot water turns into a gas and then recondenses on the mirror. That's condensation. These last two deal with sort of dry ice. Basically, if you turn a solid right to a gas, if you've ever seen dry ice, that's sublimation. And if you turn a gas right back to a solid without going through a liquid, we call that deposition.